All right, so we've been discussing this idea of forces, right? We discussed this idea of forces because when you understand the forces acting on an object, that is to say you understand the interactions and have a way to assign a numerical value to those interactions, that's what force is. When you understand the forces acting on an object, you can predict its motion, you can begin to understand what its acceleration is. And from its acceleration, figure out its displacement, its velocity, and just really understand how the object is going to interact with how the interactions cause the object to change positions in the future. A very powerful tool, and we've discussed a few types of forces so far, so just going down the list, we've taken a look at normal forces. The normal force, of course, is the support interaction between a surface and the object that is resting on the surface. This is a variable force in that it depends on what other forces are interacting with the object. The normal force responds to the other forces. We've looked at tension. Tension is another one of these variable forces, and that is to say it depends on the other interactions happening to an object. Right? There's no one singular way to calculate the tension on an object. It depends on what else is going on. So we have normal force, we have tension. What other forces have we seen? We've seen the force due to gravity. We often call this the weight, right? We've seen the force due to gravity. Maybe F subscript G, force of gravity, or maybe W. And we've defined this to have a specific value. This was a non-variable force, right? We've said this is always calculated the same way. How do you calculate the weight of an object? Mass times gravity, absolutely, mg. And there's a caveat to this. This is true so long as you're near the Earth's surface, right? You just take the mass of an object, multiply it by 9.8, you got its weight. Wonderful. We've seen other forces. We've seen friction forces, right? Friction forces. We've seen kinetic friction. Kinetic friction given by coefficient of friction multiplied by the normal force. So this force depends on another force. It depends on the normal force, and that should make sense. Both these forces, the normal force and the kinetic friction force, both of these are interactions between the same two pairs of objects. So they should depend on each other. In lab, you will see the static friction force. And as it turns out, the static friction force is an inequality. We'd say it's less than or equal to coefficient times normal force. Same form of an equation, still coefficient times a normal force. This one's less than or equal to. Those of you who took the lab today will know it's less than or equal to because as you raise up the ramp, the friction force gets larger and larger, and eventually it reaches some maximum value. But it is calculated much the same way, and oftentimes we care about the maximum static friction force, and the maximum static friction force is equal to these vessels. Again, that's something you'll see in lab. Another force you will see in lab is the elastic force, the spring force. I'll put FEL for elastic, but we sometimes call this a spring force, a restorative force. There's a number of ways to call this. You'll see this in lab. We'll probably talk about it more a little bit later, but useful force to know. All right, so we've started to understand a bunch of these different forces. Today we're going to add another force to it, but we're also going to identify a deeper way to understand one of these forces, because one of these forces I've listed on the board, we put a pretty big caveat. That gravitational force, we put the caveat that it only works, that equation only works when we're near the Earth's surface. But there's a lot of the universe that is not near the Earth's surface, right? A lot of the universe is not near the Earth's surface. So we might want to come up with a better way to talk about a gravitational force. A better way to talk about the gravitational force that does not limit us to just discussing the weight of an object near the surface of the Earth. And the story of the gravitational force. The story of the force of gravity goes all the way back. Well, I mean, technically gravitational force has always existed, but our understanding of it our understanding of it goes all the way back to Newton. Because, as the story goes, Newton was sitting under an apple tree, and he observed an apple falling nearby. Depending on the telling of the story, the apple might hit his head. But Newton observes an apple falling, and he sees the apple falling, and of course he says, well, obviously that's due to the force of gravity, the earth pulling down on it. Newton knew you could measure the acceleration of it, you could measure the mass of the apple, figure out the force of gravity. But he began to ponder further, but what about other objects in the sky, objects further above head? He thought about the moon. He said, well, the moon, there seems to be some force acting on it. How do we know there's a force acting on it? Well, the moon, if we imagine the Earth and moon system, here's the Earth, here's the moon. The moon is continually circling around the Earth. Well, a circling object is accelerating. We've seen this type of acceleration before. What kind of acceleration did we call? Centripetal acceleration. Centripetal acceleration is a type of acceleration necessary to get something to travel in a circle. It must have acceleration because when you look at the moon, at one instance its velocity might be going down and to the right. Later on in the year, if we look half a cycle later, we'll see the moon moving in the exact opposite direction. So its velocity does change, it has acceleration. That is the centripetal acceleration at work. So Newton saw this. He said, well, the moon is accelerating. And of course, Newton understands motion, right? The laws of motion are named after him. And he understood one very special law of motion. He understood the second law of motion quite well. And Newton's second law says what? Any ideas? What does Newton's second law say? Net force is mass times acceleration. Net force is mass times acceleration. So, once again, Newton looked up at the moon, understood the moon was accelerating, and by his very own law, understood that that must mean there is a force acting on the moon. But what force was it? That's the question. What force was it that was getting the moon to move around in a circle? Well, Newton said the Earth pulled the apple down. If the apple was higher up into space, the Earth would still pull the apple down. So it makes sense that even further into the space, at the location where the moon is, there must be a gravitational force acting on it. And that gravitational force must be what's pulling the moon towards the Earth. That sounds reasonable, right? Gravitational force is what pulls the moon towards the Earth. Now, from here, Newton made a couple of guesses, we'll say. He said, the moon is pretty close to the Earth. And there seems to be a lot of interaction between the moon and the Earth. So he reasoned that that is probably a pretty large force. But when you look at the Earth and the sun is much, much, much further away. And there doesn't seem to be as much interaction between the sun and the Earth. This is evident by high tides and low tides. The moon affects the Earth quite drastically, as seen by the tidal forces that occur on Earth. But the sun doesn't do the same behavior. So Newton reasoned that this gravitational force must be inversely proportional to the distance between the two bodies. The Earth and moon, the Earth and sun, whatever it is we're looking at. The closer two objects are, the stronger the force must be. And he went a little bit further, having an understanding of three-dimensional geometry and a whole bunch of other stuff. He reasoned it must be proportional to r squared. This is not at all obvious, but it does come from some mathematical principles that we'll take Newton's word. All right. Newton went a little bit further too. He said, well, there are different objects in the sky, and depending on how large those objects are, we'll probably see different forces. And he reasoned that the larger the objects are at play here, the larger the forces must be. So he reasoned that two objects of more mass probably have a larger force between them. So he said the force of gravity must be proportional to the mass, right? And he said, well, it probably depends on the mass of the Earth. And it also probably depends on the mass of the moon. And you can look at other celestial objects and see different moons of differing masses, and that different moons must have different forces acting on them. And he came up with this relationship. Well, with all of these proportionalities, you can create an equality. You can always create an equality from proportionalities by inserting a constant of proportionality. So Newton said, taking all of this and combining them together, the force of gravity must be equal to some constant, then why don't we use capital G? Capital G for gravity. So a constant proportionality, G, multiplied by mass of Earth, mass of Moon, divided by the distance that separates them squared. And in the time of Newton, we had a decent understanding of how far apart the Earth and the Moon were. We had guesses at what the mass of the Earth is in total, but we had no idea what the mass of the Moon is. And since we didn't know what the mass of the Moon is, we could not take this and solve it and figure out what that constant G is. It was just impossible at the time. This is as far as Newton could have gone. Well, actually, we can take it one step further. Because the Earth and the Moon, they're not that special. They're just two rocks floating in space. We could substitute this with any two objects. We could say, this is object 1, object 2. Again, the Earth and the Moon, they're not special. They're just two rocks in space. Since they're two rocks in space, we could say more generally that the force of gravity between any two objects, doesn't matter how big, how small they are, the force of gravity acting in between any two objects must be that constant times mass 1 times mass 2 divided by r squared. So it doesn't actually matter if you know what the mass of it is. You can figure it out from any two objects. But this force is going to be so small that it's hard to tell with masses that are measurable on the Earth's surface. So this really is as far as Newton got. Newton got as far as defining this relationship, did not have a value, did not even have a guess at what that constant G is. But he defined this relationship. And this relationship becomes Newton's universal law of gravitation. Universal law of gravitation. And unlike our other equation for the force of gravity, the weight, mg, this works everywhere. It's universal. It works anywhere in the universe, anywhere in the known universe, we might say. All right, well, fast forward about 150 years. We arrive in England in the 17th century, I believe. And during this time, a physicist of the name Cavendish finally got equipment that was precise enough to undertake an experiment where what he did was take two large lead spheres, hundreds of kilograms large, very heavy. Cavendish took two large spheres, measured the distance between them, and this is important, it's the distance between their centers. He was able to measure the distance between their centers and found the force acting on these lead balls. How did he find the force that was acting on these lead balls? Well, he found them by measuring the acceleration. And from the acceleration, he was able to figure out the force. It works in reverse, too. If you know the acceleration, you can figure out the interaction. And that's what he used to do. So Cavendish measured the radius, understood the masses of the two objects, and from there, he calculated out what this gravitational constant is. He said, well, if I know the force, and I know the masses, and I know the radius, then the gravitational constant that Newton predicted would be that force that you calculated, the force of gravity, multiplied by the distance between the centers of the object squared, and divided it by the mass of object 1, the mass of object 2. So Cavendish did this. And during his experiment, he got a relatively precise number. Well, relative. At the time, he found that it was about equal to, I'm going to use an equal sign with a squiggly over it to say it was about equal to. He found this constant to be about equal to 7 times 10 to the minus 11. And what are the units? The units are Newton from the force, meters squared from the radius, divided by mass 1 and mass 2 kilograms squared. That's what Cavendish found. And this was remarkable. This is a remarkable feat because that number is so small. 10 to the minus 11, that's 0.00000000007 Newton meters squared per kilogram squared. Very small number, very hard to measure. That is why Newton could not do that in his time. It took a century and a half to get the precision necessary to make this measurement. And in the preceding century since, we found a closer value for the universal gravitational constant, we call it. Why do we call it that? Well, it's the constant in the universal gravitational equation. So we found a closer value for this universal gravitational constant to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Cavendish was not all that far off. I think we have a few more decimal points after that, but we'll round. Cavendish was not all that far off with his estimation as to what the universal gravitational constant is. But we found this value. And this gives us the force of gravity anywhere in the universe, whether you're near the Earth's surface or whether you're off into the middle of space. This equation will always work to give you the force between two objects. So we say the force of gravity. No, don't want to just say mg anymore. Although mg will still always work near the Earth's surface. Instead, we want to say the force of gravity is given by this universal gravitational constant multiplied by the two interacting objects, mass 1 and mass 2, divided by the distance that separates them, quantity squared. So when we put this into action, we say, okay, well, let's say I have a few measurements. Let's say I want to go back to analyzing the Earth and the Moon system. Because this is what Newton was originally looking at, the Earth and the Moon system. So we'll complete Newton's analysis and then learn something about these two objects. We complete Newton's analysis by saying, well, acceleration here, that is acceleration that causes an object to spin in a circle. Remind me again, what do we call that acceleration? Centripetal acceleration. So we can say that this force, I'm going to leave a little bit of a room here to put a subscript in a moment. We can say that the force is given by mass times this centripetal acceleration. And this is true for a force that is getting anything to move in a uniform circle, meaning not speeding up, not slowing down, just going in a circular path. This force, since it's related to the centripetal acceleration, well, we'll give it a special name. We'll call this the centripetal force. So what is the force that we use to describe an object that is moving in a circle? Well, an object that is moving in a circle is feeling a centripetal force. We ask, what is the direction of it? If you remember, when we defined the centripetal acceleration, we said the acceleration is always inward facing to the center of the circle. In fact, that word centripetal is Latin for center seeking. So your centripetal acceleration is inward. Your force points in the same direction of your acceleration. This is always true. your net force always points in the same direction of your acceleration. So your centripetal force is always pointed inward as well. We call it the center-seeking force. And when we have this understanding, we take a look and we say, well, that makes sense. This makes sense that the centripetal force should be inwards, because we know this is a gravitational force. And we know that the Earth always uses its gravitational force to pull objects towards it. And we see that our forces are always pointed towards the Earth. So it kind of matches up with our understanding. That gravitational force should always be pointed towards the Earth. The centripetal force is always pointed towards the Earth. They match up. And they should. They should, because that gravitational force is what's causing this centripetal force. All right, well now we think back to when we talk about centripetal acceleration. We think way back and we say, well, centripetal acceleration, it depended on what? It depended on the speed the object was moving at, right? And it depended at the radial distance. If you go back to those little note cards I gave you, you have a centripetal acceleration equation that says centripetal acceleration is v squared over r. So that means your centripetal force mv squared over r, where r is the radius of our circle, and v is how quickly our object is moving. Now this does not only pertain to the Earth and Moon, this pertains to any object that is moving in a circle. Any object that is moving in a circle must obey this centripetal force equation. Any object that is moving in a circle must obey the centripetal force equation. We feel okay about this? All right. So this gives us a basic understanding of the centripetal force. But then we say, okay, well, what is causing this? And again, what is causing this for the Earth and Moon is the gravitational interaction between the Earth and the Moon. The gravitational interaction between the Earth and the Moon. So we say, force of gravity is described universally by gravitational constant. The gravitational constant 6.67 times 10 to the minus 11 Newton meter squared per kilogram. And then the general equation, we would write out m1 m2 over r squared. This is the general equation. We can make it fit our specific scenario by changing m1 and m2. We say, what am I looking at here? I can call Earth m1, m2 could be the moon, so I can say the force of gravity equals g times the mass of the Earth times the mass of the moon divided by r squared. Again, this is what Newton reasoned, right? We're just going back to Newton's reasoning about what that gravitational force is. We look at our centripetal force and we say, well, if we're looking at the moon and we want to understand the motion of the moon, that mass is going to be the mass of the moon, mv squared over r. We feel okay about this? Any questions, any thoughts, any comments? So what we can do from here is combine these two equations. We can combine these two equations because the gravitational force is the centripetal force. Remember, centripetal force, it's just a generalized term we say is a force causing an object to move in a circle. If you're twirling a ball around on a string, the string is causing a tension. That tension is your centripetal force. So centripetal force is kind of like a general term to say this is the force causing the circular motion. The actual name for that force here in this instance is the gravitational force. So we can take these, set them equal to each other, and that would tell us the gravitational force, mass of the moon, mass of the Earth, divided by r squared, the gravitational force must equal the centripetal force. And what do we notice about this? We notice, yes? Absolutely, both sides has the mass of the moon. Both sides has the mass of the moon, so that'll cancel out. We're left with gravitational constant, mass of the Earth divided by r squared is equal to v squared over r, where v is the velocity of the moon. How fast the moon is moving. All right, what do we notice next? There's at least one factor of 1 over r on each side, right? So that means at least one factor of these 1 over r's cancel out. That gives you gravitational constant is mass of the Earth over r equal v squared. Sound all right? So here's what we'll do. We'll see how good is this law? How applicable is it? Let's find out. The moon takes how long to travel in one complete circle? Who knows? A month? About a month? Can we be a little more precise? Who knows? Actually, I think it's, 27? 27.3? Hold on. We'll use, it rounds down. 27 days. Sorry, 28 days was on my mind because I'm planning on watching 28 Days Later. But 27 days. 27 days is about the time it takes for the moon to go around the Earth. Okay. Well, if that's the case, then we can find the speed the Earth is moving at by taking distance. One circle is 2 pi r in distance divided by the period. So we can figure out the speed of the moon, right? That's good. That's one of the pieces of the equation. That tells us the velocity. Square that eventually. Cool. Then we need some other pieces of information here. Let's say we are given the distance to the moon. The distance to the moon is 384.4 million meters. Oh, you guys do it that in a second. So we have the distance to the moon. Wonderful. So that gives you g, a way to calculate the velocity, and the distance r. My question to you is utilizing Newton's universal law of gravitation. I want you to give me a quick calculation of the mass of the Earth. Let's go ahead. Let's solve it out. You should have all of your values. Now this is going to test your abilities to plug things into a calculator because there's some absurd numbers here. 10 to the minus 11. Got a 10 to the 6 million. Keep in mind that we want SI units of seconds, not days. Sounds pretty close. All right, who wants a little more time? You guys have it. Again, I want you to practice utilizing your calculator so we don't make those calculator mistakes when we start dealing with these odd numbers. Okay, so let's go ahead and take a look at this. I started doing the derivation here, right? Mass of the Earth is equal to v squared r over g. All I did here was multiply over the r, divided the g. We could go a step further. We can plug in 2 pi r over period for v. Doing your conversions from 27 days to seconds, doing your conversion, writing in the million part, the 10 to the 6 million. What you should find is that when you plug in everything, you end up with a number of about 6 times 10 to the 24 kilograms. So you ask, well, how accurate is this? How good is Newton's universal law of gravitation? How well does it make these predictions in actuality? And the answer is very accurate. What is the mass of the Earth, you might ask? The mass of the Earth is 5.97 times 10 to the 24 kilograms. That's just a hair under 6 times 10 to the 24 kilograms. And in fact, the difference might be coming about from the fact that the period of the moon is actually 27.3 days. A little bit longer would decrease this value that we got. But even with that 27, you end up with a very, very accurate mass of the Earth. Does that sound all right? So we find Newton's universal law of gravitation. And utilizing Newton's universal law of gravitation, the distance to the moon and how long it takes the moon to go in a circle, we're able to estimate the mass of the Earth quite accurately. More accurately than we were able to prior to this discovery. More accurately than prior to this discovery of the gravitational constant, because before that we had to use an estimation of what the density of the Earth is, and use volume and density to figure out mass. This is much more accurate. It gave us a value dead on with what the mass of the Earth is. Now we go on to say, well, this is the universal law of gravitation, right? Universal law of gravitation should work everywhere. It should even work right here on the Earth's surface. So we ask the question, does it match up with what we would expect from the Earth's surface? Let's find out. So the next scenario we're going to take a look at, the camera. The next scenario we're going to look at is the professor standing on the Earth. So I have a mass of about 100 kilograms. Or less than that, but let's use 100 for the sake of ease in calculation. So we'll say it's 100 kilogram on the dot. 3 sigmas. We're going to use the mass of the Earth that we found earlier, 6 times 10 to the 24 kilograms with 2 sig figs here. And we are going to use the radius of the Earth. The radius of the Earth is 6,400 kilometers, or 6.4 times 10 to the 3 kilometers. Going to have to convert to meters, but let's hold on. So the question is, with how much force is the Earth pulling me down? And we can do the traditional, take my mass, multiply by 9.8, find the answer, but let's take a different route. This time, let's use Newton's universal law of gravitation. Newton's universal law of gravitation says that the force of gravity is given by gravitational constant 6.67 times 10 to the minus 11 Newton kilogram squared per meter squared. No, kilogram times meter squared per 6.67 times 10 to the minus 11 Newton kilogram squared per meter squared. So we have our universal law of gravitation, G times the mass of the two objects multiplied together. That's going to be the mass of the Earth and the mass of, well, me. And then we divide that by the distance between myself and the center of the Earth. Technically speaking, it's the distance between my center and the Earth's center. But the, meter, less than a meter between me and the Earth's surface, pales in comparison to the distance between the surface of the Earth and the center of the Earth. So it doesn't make a difference if I add my central distance to the floor into that radius distance, because it's not going to change that value significantly enough to notice. Well, what I want to do is rearrange this a little bit. I want to rearrange this instead of plugging values in, just for the sake of making an observation. I want to combine that universal gravitational constant, the mass of the Earth, and the radius of the Earth. I was using capital R there for radius of the Earth. I want to combine those three pieces and separate out my mass. And now what I'm going to ask us to do is let's calculate the value of what's in the parentheses. Take that gravitational constant, multiply it by the mass of the Earth, 6 times 10 to the 24 kilograms, and divide it by the radius of the Earth, 6,400 kilometers, converting to meters, of course. So calculate out that value of what's in the parentheses here. G times ME divided by RE. What do we get when we multiply those three values together?
6.25 times 10 to the 7.
Did I get a value wrong here? Mass of the Earth.
10 to the 7. 2 plus 6 times 10.
Oh, so sorry. R squared, what am I doing? I messed up Newton's law of gravitation. You'd be so disappointed. Sorry, let's try that again. Because this should be a very familiar problem. So when you plug in your values here, what do you end up with inside of the parentheses? What do we get? 9.77. What does that round to? 9.8. 9.8. We've seen that value 9.8 over and over. We get the force of gravity is 9.8 times my mass. That 9.8 is the acceleration due to gravity. We end up back at that original equation where we take the mass of an object, multiply it by 9.8 meters per second squared, and you can figure out the weight, the force of gravity. So this equation does, in fact, reduce down to our familiar equation for the force of gravity on the Earth's surface. 9.8 meters per second squared. If you ever wondered, where does that 9.8 meters per second squared comes from? Well, it comes from this constant, the mass of the Earth and the radius of the Earth. If the radius increases, meaning you travel higher up in elevation, you would see a decrease in weight. And that is what you would experience. You go climb to the top of Mount Everest and feel ever so slightly lighter than you do right here in Rancho Cucamonga. If the mass of the Earth was suddenly to increase, well, that force of gravity would become a lot stronger. You'd feel a lot more weight. So it reduces down to this. If you want to ask what the force of gravity is on the 980 newtons, there you go. Sound all right? So we move on to ask the question next. We ask the question, what is the behavior of any object near the Earth's surface? So here's the Earth's surface. What I am going to do is place 3 objects near the Earth's surface. We have a marker. We have a piece of paper. And we're going to have a folder. We'll space them out. Each of these objects are going to be some distance from the radius of the Earth that is about equal to the radius of the Earth. The small amount of distance between the object and the surface of the Earth is going to be negligible because the radius of the Earth is so large. So we place these 3 objects near the Earth's surface, and we ask, well, Newton's second law is useful because it tells us about the acceleration of an object. So let's say I wanted to know the acceleration of the marker, A subscript m. The acceleration of the marker would be given by the force acting on it, and that would just be the gravitational force, divided by the mass of that marker, m subscript m, mass of the marker. Does that sound okay? We expand out this force of gravity. We say force of gravity is g, mass of the marker, mass of the Earth, divided by the radius of the Earth squared. Don't want to make that mistake again. Divided by the mass of the marker. Suddenly, the mass of the marker cancels out. You end up with the acceleration of the marker is g times the mass of the Earth divided by the radius of the Earth, quantity squared. We just calculated that out to be 9.8 meters per second squared. This is the derivation for why the acceleration of a falling object is constant near the Earth's surface. It does not depend on the mass, because the mass cancels out with the mass that is inside of this gravitational constant. You do the same thing with the folder, perhaps, and you'd find the acceleration of the folder is 9.8 meters per second squared. And then ask the question, well, how accurate is this? Perform an experiment. You can take a marker, drop it, see it fall. It falls at some rate, right? You can measure out the distance. Well, that should fall at the same rate as a folder, much heavier. Take these 2 objects, we see, do they hit the ground at the same time? Yeah, seem to, right? So you say, okay, wonderful. We did the same thing with the paper, acceleration of the paper. And if our estimation here is correct, the mass of the paper cancels out too, giving us the acceleration of the paper should be 9.8 meters per second squared. Should be the same as the folder, should be the same as the marker. So here I take the paper, here I take the folder. I'm going to drop them We're going to see, do they hit the ground at the same time? Not even close. Not even close. Why?
Air resistance.
Air resistance. Air resistance. There's a second interaction going on here that we are not accounting for in this acceleration of the paper. There's a second interaction going on here that we're not taking into account. And that is a new interaction called air resistance. So we will define a force called the force of drag. The drag force. So what is the drag force? Here's our piece of paper. Nice flat sheet of paper. And what the drag force is, it's an interaction between the molecules in the air and the paper itself. It's an interaction between the molecules in the air and the paper itself. Here are the molecules. They bounce off the paper. When they bounce off the paper, they go through a collision, imparting a little bit of force. And since there are, Avogadro's number of air molecules here, the force becomes quite substantial to the point where this piece of paper begins to slow down its acceleration. So it's an interaction between the air molecules and the paper, and very specifically, it's an interaction between the air molecules below the piece of paper and the paper itself. The air molecules above the paper don't cause any effect, just the ones below. And we can prove this. We can prove this, and I'll prove this by performing the same experiment I just did, but this time I will remove all of the air molecules below the paper. So I take a big pump, I pump out all of the atmosphere from this room, and we all suffocate. Now, I'm going to do it a different way. Instead of dropping the two side by side, I'm going to place the paper above the folder. And what does this mean? This means that there's no air below the paper, there's only folder below the paper. Right? So I've effectively removed all of the air below the paper. We see, do they fall at the same rate? The answer is hopefully. I don't know if there's so much roundness here. So we see, do they fall at the same rate? And lo and behold, they do. Because you remove the air below the paper. This is a proof of what the interaction is between. It's between the molecules and the paper. Sound good? So we go on to ask more questions. Okay. What might the force of drag be proportional to? Well, the more molecules there are, the more collisions are going to happen, the more force we would expect, right? So the more molecules, the number of molecules that are present is probably one of the dependencies here. The more molecules that are dependent, the more molecules that are present, the more air resistance we would expect to see, the larger the drag force. I'm going to use density to substitute in. This is the density of the fluid we are traveling through, the density of the air in this case. Density is mass divided by volume, just the same as it is with any solid object. So we'll say this is the density of the fluid, and I'm using fluid very specifically because it could be a gas, it could be a liquid. Sound all right? So it should depend on this density. Okay, well, what else does the drag force depend on? Well, if our paper was larger, right? If we had a larger area, well then surely we would be catching more air molecules, right? So the larger the area, the more drag force that is present. That's why parachutes are quite large. They're quite large to catch a whole bunch of air molecules as you fall towards the earth. So the force of drag probably then depends on the area of this object. Sound reasonable? All right. What else do we suppose it depends on? Well, Perhaps it depends on the speed it's traveling at. If it's traveling slowly, then it's hitting fewer air molecules per second than if it were traveling fast. So if it is traveling slowly, then it hits fewer air molecules per second than if it is traveling quickly. So perhaps it depends on the speed. And empirically, we do experiments to find that it actually depends on the speed squared. All right, we take all of this, we put it together. And we say that then the force of drag must be equal to some constants, and I'm actually going to put in 1/2 of a constant. 1/2 C. In fact, C subscript D, we put C for constant, D for drag. This is our drag constant or drag coefficient. We say the force of drag is equal to 1/2 this coefficient of drag. Why do we put the 1/2 there? Well, we do for historical reasons. Technically, we could build the 1/2 into this coefficient of drag, but we choose not to. We choose to continue this 1/2. What else does it depend on? Density, area, speed squared. And this gives you the force of drag acting on any object that is moving through the air. And then we ask, well, what is that coefficient of drag? What is CT? Well, that depends. It depends on the situation that you're given. Because this coefficient of drag is what describes essentially the aerodynamics of whatever object is moving through the air. Something that is more aerodynamic experiences less drag force. And it does that because this coefficient of drag is smaller for more aerodynamic objects. This coefficient of drag becomes smaller for objects that have a more like triangular face rather than a flat paper. So this coefficient of drag depends on the aerodynamics. There's not one singular value, rather there are many values. Typically, the values for this coefficient of drag somewhere around value 1-ish. Okay. Are there any questions, any thoughts, any comments? Because we're going to take this and combine it with this gravitational force. We're going to take these two things, combine them together. And we're going to do so in an example of a squirrel falling from a tree. Because there's some interesting physics that come into play. So we're going to say a squirrel falls out of a tree. A squirrel falls out of a tree. As the squirrel falls, it will experience two forces. As the squirrel falls, it experiences two forces. What are those two forces it will experience? Gravity is one of them. Gravity points in which direction? Downwards. And we have drag force upwards. So we have force of gravity down, drag force going upwards. Sound good? Now, initially, when the squirrel falls out of the tree, this drag force is quite small. Because initially, when the squirrel falls out of the tree, the velocity is close to zero, right? Because it starts at zero and then it has to speed up. So initially the drag force is quite small. But as the squirrel falls further and further, the drag force increases because the squirrel is speeding up. So the drag force increases as the squirrel speeds up until the point where the drag force becomes equal to the force of gravity. And something interesting happens here, because when the drag force is equal to the force of gravity, what do we know about the acceleration? It's 0. Because our forces are in balance. Our net force is 0. Our acceleration must be 0. And since our acceleration is 0, our velocity, does it increase, decrease, or stay the same? Stays the same. So that means we reach this point where our squirrel will stop speeding up and be at a constant velocity v. Meaning that our force of drag will start small and it will increase until the point where our drag force is equal to our force of gravity. It increases until the point where our drag force is equal to our force of gravity, at which point we no longer speed up, and this is the moment that we call, or say the object is in, what was that? Terminal velocity. We have reached terminal velocity. So we say 1/2 coefficient of drag multiplied by the density of air multiplied by the cross-sectional area of our squirrel multiplied by the terminal velocity squared, that is all of our drag force. And we set that equal to the force of gravity. And of course, as we know, the force of gravity must be gravitational constant multiplied by the mass of the Earth multiplied by the mass of the squirrel divided by the radius of the Earth squared. Now, could we reduce that to 9.8? Yeah. Squirrel's probably near the Earth's surface. I don't know of any squirrels that aren't. So we get this relationship for terminal velocity. Now, this is true of all objects. It's not just true for our squirrel. You just have to substitute mass of squirrel in for mass of whatever object we're looking at. But this is the equation that tells us the relationship for our terminal velocity. I'm going to move over here. I'm worried that's a little bit hard to see for some of us. All right. So let's go ahead. Let's first make the assumption that we're near the Earth's surface. This will reduce down our equation quite a bit. So we're going to make the assumption that we are near the Earth's surface. Rho a v squared is equal to mass times 9.8. So we reduce universal's law of gravitation to being specifically near the Earth's surface, where the acceleration due to gravity is 9.8. We then take this and we solve for, we're looking at the terminal velocity, we solve for the terminal velocity, which would equal what? Square root 2 times, for us, the mass of the squirrel times g, divided by density of the air multiplied by the area of the squirrel. Okay. So we plug in some values. The density of air is about 1.2 kilograms per meter cubed. 1.23 something. We'll estimate 1.2. Sound good? Squirrel, our squirrel friend, will have a mass of, oh, I forgot my coefficient of drag. Hold on. Coefficient of drag. Coefficient of drag. Our squirrel friend will have a mass of about 250 grams. Squirrels are relatively light creatures. You all right about this? We need a couple more values. Coefficient of drag for a squirrel falling can be estimated to be about 1. Technically, I think it's closer to 1.1 or 1.2, but we will use 1 here for value. Also depends on the species of squirrel that is falling. And then we ask the area. The area for our squirrel will be estimated to be a rectangle. We are estimating our squirrel to be a rectangle. Is this a great approximation? Not really. But we will estimate it to be a rectangle of size. Here's our squirrel head. A rectangle will be of size 10 centimeters by 5 centimeters. No, wait, was that right? No, that's way off. Hold on. Sorry, I did my unit conversion in my head and I got it slightly off. Slightly, by quite a bit. 40 centimeters by 10 centimeters. That was the estimation I wanted to use. Okay. So we have an area, a rough area. Coefficient of drag, mass, and air. My question is, what is the terminal velocity of our squirrel friend? How quickly is it falling? Remember to convert to kilograms and to meters. Who's answer? Who has the terminal velocity of our squirrel? Who wants a little more time? All right. So you time the values, you plug them in, you should find the terminal velocity of your squirrel to be about 10 meters per second. 10 meters per second. That sounds a little bit fast, but that would be about the speed you would be traveling at if you fell for 1 second in time. This is the speed, the maximum speed a squirrel can fall at. And in fact, this speed for a squirrel is survivable. A squirrel can survive a fall hitting the ground with 10 meters per second speed. And why is this interesting? Well, this is interesting because a squirrel can survive hitting the ground with this speed. This is the maximum speed a squirrel can fall at. That means a squirrel can survive a fall from any height because of this terminal velocity. Squirrels can survive falls from any height. And generally speaking, mammals smaller than squirrels will also be able to survive falls from their terminal velocities. Mammals larger than squirrels, not so much. Okay. Are there any questions, thoughts, comments, concerns? Are we all happy that our squirrel survives the fall? Okay. So we'll end it there, a whole 2-ish minutes early. If you are in the Wednesday lab, your problem set 4 is up here. You can grab it on your way out. And if you have any questions, feel free to stay behind. Problem set 5 is due on Wednesday. Problem set 6 is online and due next Wednesday. Next Wednesday, we also have our next exam coming up that will cover forces and Newton's second law.